We're going to talk about torque today. So to understand the concept of torque, let's try to picture a situation, or you can stand up and try these actually situations. So I have three different cases when a person is trying to open a door by forcing on further edge of the door. Further edge, I mean further edge from the hinge right here. So let's say applied force in here, and then we have a different situation where we apply the force a little bit closer to the hinge. So force is right here, same force, same person applying a force, but this time the force is actually pretty closer to the hinge of the rotation of the door. So, and then finally we have the person pushing the door, trying to open the door by forcing the door kind of perpendicular to the axis of rotation. This is the axis of the rotation, which is the hinges. Now let's try to see this in a more interesting version. We call it bird eye view when you're looking from the top. So suppose this is the, okay, here is the hinge of the door from the top, you're watching it, and so this is the top part of the door, and then what you see, you're seeing a force being applied on this edge force. Okay, so the door will be rotating, in fact, this direction. Okay, so I just want to make sure that you understand that the force also could be applied to any other different direction, but for now we're going to focus on, let's say, perpendicular to the door direction force. Now let's look at the second situation where we again have the door. Okay, and we have the hinge right here, and then we have the force applied right here. Now finally, okay, so again rotation is gonna go this direction, and then finally let's do the door again. Here's the hinge, and then the force is being applied this way. So for a moment, either you stop, pause this video and get up and then try it on the door, or just I'm pretty sure from your personal experience you would know that the third situation, I'm gonna call this one a third situation, is actually will never open or rotate the door. So on a second situation, you will have a little bit hardship to open the door. You have to apply more force to actually rotate the door. And you won't even believe how hard it is until you try it. Just get up and try it. So when you open when you apply the force the furthest away from the from the hinge, which is the first situation, then you will see that the door will open easily. So what does this mean? It means to open or rotate a door, the only force is not enough. It is also important where you apply it and at what angle. So let's define a new quantity that will describe the cause of rotation. So I want you to remember that the cause of motion is the force, and torque is the analog of force for rotation. So if force causes the motion, linear motion, or and the torque then causes rotation. Okay, well, to do so, let's actually make a little bit more general case. Suppose that you have a rigid object. Okay, so here's the rigid object, and rigid object, let's suppose it's rotating about the axis O, and then axis O is coming off of the of the board, and suppose like we want to apply a force on point P. Okay, so here's the force that is being applied on point P. Okay, so I'm going to call it force F. Okay, and let's see, that is making a certain angle with the horizontal, and I'm going to call it a phi, angle phi. So we are going to call from rotational axis to the point P that we have, and obviously I forgot to put the point P right here, so you know that. So I'm going to call this distance from 0 to P, O to P, as the radius, so position vector, as you may want to know. Or so we want to describe define the torque as first of all, let's denote the torque. Torque is denoted with the Greek letter tau. Okay, this is how you write the tau. Okay, it's like a T, but the top part is gone. So, and then define the torque. So we say torque equals R times F times sine phi. Okay, so which means F sine phi, if you see, that's a tangential component. So if you want to, let's try to understand what is the tangential. So if I bring a perpendicular to the radial direction, so that would be F of the radial component, and so perpendicular to the radial axis, that would be the tangential. So F tangential. So it's a tangent to a point P. Now, in other words, I can say torque equals R and F tangential. So in your book, you will see the vector version of this, and which is pretty much also the same. Now the torque is measured in newtons times meter. It's a derived units because it measures with the R being a meter, force being a newton. So now let's try to kind of see what happens to the Newton's second law in rotation. So we know that if there is a force applied, there should be an acceleration. So I'm going to write F net according Newton's second law equals mass times acceleration. So if I'm talking about the force net, that's the only tangential component of the force is going to provide the acceleration. So I can say F tangential equals mass times A, absolutely, you're right, tangential acceleration. Okay, so from the other end, I can say that okay, now from the definition of F tangential, from here, I can say F tangential equals torque over R. So I'm going to plug that in here. So I have a torque divided by R equals M A tangential. Okay, so and then also we know that A tangential equals alpha times r. Okay, so I'm going to plug that in as well and then solve for t. Tau. Torque equals mr times alpha r. So that would be mr squared alpha. So let's recall, what is the mr squared? And yes, you're absolutely right. That is moment of inertia, I alpha. So we end up having torque equals I alpha. Well, if you look at this, we know that the equivalent of torque in a motion is the force, and alpha is kind of analogous to the mass, and alpha is analogous to the tangential acceleration. So therefore, this is Newton's second law for rotation. It's no new law, it's the law that you already know.